So, in this lecture, we will talk about the sintering of iron ore, and the concept that will be covered. First of all, I will talk about what is sintering, and then sintering machine, temperature profile in the sinter bed, condition of matching. Matching is a very important phenomenon in sintering, and sinter mineralogy. Now, sinter of iron fines. Now, what do you mean by the sintering? In the sintering, what happens is that we take the iron ore fines, but not very dust fines. It has some limit, that is around 0.5 millimeter and above. Okay, so the fines, iron ore fines mixed with some amount of the coke bridge, that is the iron ore fines. What is happened is that iron ore fines, you heat it to a very high temperature, as I said, then the particle incipient fluid, that is the incipient, your fusion take place at the particle surface and particle get agglomerated, okay, by mostly by the fusion bond. And also some new crystallographic phases also appear in case of the what is that called sinter. When you make the basic sinter or flux sinter, then the calcium ferrite form, new phases form. Okay, they also, these crystallographic phases, these crystalline phases also can hold the particles together very strongly. And not only that, they will also provide a lot of reducibility. So basically, the sintering is basically you are heating the iron ore fines at a high temperature and bond them by fusion bond as well as diffusion bond, okay, through by atomic movement and so crystalline formation and all this. So, think is the sintering is a process where iron ore fines are heated to a high temperature to partially fuse and form a strong agglomerated mass of iron ore called the sinter. Second thing is, this is the basically the machine that is used for the sintering is called duet Lloyd type sintering machine. This machine is usually used into the copper industry for preheating the copper ores basically. Now, this machine now used for all sintering purpose also. Now, what is this machine is that you can find there is an endless belt of pallets. What are the pallets? Pallets are basically a rectangular box, okay, and they are situated over chains, and this chains basically, and they move in a move in this way, and that the chain continuously revolve around these pulleys, okay, along with the pallets like this. So, here is the pallet. What you do in the pallets, you basically take the raw material, okay, you first take the raw material and then it is ignited from the top. First surface you get ignited, after that and when you ignite it, basically that gets agglomerated, right, and but across the bed you have to have a sintering. So, this fire line has to be crossed through the bed to the bottom, and if it cross through the bed, and then all portions will get sintered. Now, first of all, what are the raw materials that you used? First is the fines, okay, these are the fines that you raw material fines. There's the iron ore fines is ranging from 150 micrometer, that means 0.15 millimeter, right, to 5,000 micrometer, that means 5 millimeter. So, around 0.15 millimeter to 5 millimeter, this is the range, maybe 0.1 millimeter to, you can say, 5 centimeter, 5 millimeter size, okay, these are the size of the particle. And also you use, so you do not use a very fine here, because if your particles are very fine, less than 150 micrometer, you cannot do the sintering. I will come to that, because as you see, there is a sintering take place through the bed, and you basically you suck a hot air through the bed and you do the complete bed sintered, okay. So, there is a gas flow through the bed. So, you should have sufficient permeability. If you use too much of fines, that will obstruct the gas flow. So, that is why the fines are not allowed. It may be maximum 0.15 or 0.2 millimeter, not less than that, right. Then you use the coke bridge also, coke bridge 4 to 8%, and their size is also 3 to maximum your 3 millimeter like that. And also you use limestone, basically lime you use, basically lime also 3 millimeter size, very as a flux you use it, and water 5 to 20% maximum in this range. So, these the raw material beans are there, and then all the raw material beans come, and there is a mixing drum is there it get mixed up. And why this mixing is there? During the mixing, basically we make some micro pellets type of thing, very small balls or granulated material, because as I said, the sintering takes place by sucking the air through the bed. So, unless you bed has sufficient permeability, it will have problems. So, basically we granulate in the mixing drum, we granulate this mixture and then it is charged on the pellets. And you can find there is the ignition hood and you ignite. Who ignite the top surface? Which material get ignite? It is the coke bridge. Coke bridge is given there around 4 to 8%. That coke bridge get ignited and generates the heat, right? So, but at the top you first ignite the coke bridge, that is what is there, and then your top surface get heated up. That is called the flame. There is that heated up and top surface gets sintered. And then what you do subsequently, you take out the air from the top surface. You suck the air. You can see there are wind box. These are called the wind box, right? These are called the wind box through which you suck the air from the top to the bottom, and then this air moves through this bed, and this fire line progressively move. That is the as it moves down, because what happens, the hot air comes in, it preheats the there is a sinter mix, the layer below the combustion zone, and that zone also attains, and also in that zone when it is preheated significantly, then the coke bridge in that zones again get fired. Okay, so the fire line basically moves to the layer below, and then again when the air pass through this combustion zone, it gets hot off, it gets heated up, and then when it passes through the layer below it, it preheats those sinter mix. That also get preheated, and when preheating is significant, the coke bridge in that layer again get ignited. That way, that is called the fire line slowly moves down, right? Slowly moves down, and finally complete sintering takes place. And it is very similar to puffing a cigarette, right? You just ignite the top surface, and then as you puff the cigarette, the fire line moves slowly at the bottom. So, similar thing here also takes place, right? So, here you can get the sintering take place, and then you can find there is a dischargeant. Here the pellet comes, and here is the dischargeant where the sinter breaker is there, it breaks and goes out, and the chain comes down here, and then again it comes freshly here, and again sinter mix is put. So, it is a continuous process, okay, and it is an endless build of pellets basically, and one pellets come, you charge the material, ignite it, and then it goes through this process of in this process of sintering across the bed, and then it is discharged from this end. So, this is the way the sintering is done, right. Now, you understand the temperature profile in a sinter bed is very important, and it is basically the schematic of sinter bed after few minutes of ignition at the top, and it is a fixed bed. It is unlike in the plant. In the plant basically there is a forward movement of the pellets. Here, if it is not in the laboratory scale, you can have a fixed bed. Your pellet does not move, okay. And obviously you must understand in the every pellets is grated, like this type of graters through which the gas can come out to the wind box. So, here the sinter material is there, but here in this case you can find this bed does not move in the horizontally, unlike into the. So, it is that's why it is called a fixed bed, and it is basically done in the laboratory scale. And why I am showing it, because in the laboratory scale you can have a thermocouple inserted inside the bed, and you can measure the temperature at every location from top to the bottom. So, and then so across the depth of the bed you can measure the temperature, and you can see this type of temperature profile just after few minutes the ignition at the top. After you ignite the top and you just start sucking the air, and then you can see after some time when the combustion zone is here, your temperature profile will look like this. This is the temperature profile. You can have the cold sinter, because what happens, the air is coming up. So, air basically top sinter, because sinter will be cooled up by the air, and in the term that the air will be get preheated. So, then what happens, this is the hot sinter also. It is basically in this when the combustion zone is here, just above layer will be some of the hot sinter will be there, because some heat exchange is taking place, not complete. So, that is why still they are hot. And then this is the combustion zone, here is the maximum temperature, is peak temperature you can find, and here also gas passes through it, and gas preheated maximum here. And then in this layer what happens, the gas release the heat to the solid get preheated just below the combustion layer, the solid get preheated, and in the next moment if you see the next time, this layer will get again here combustion will take place. So, combustion zone will move downwards, right. But at a particular just after starting of the preheating zone, these are the situation, cold sinter, then hot sinter, and then you have a combustion zone solid, and then preheated zone, because here the gas is supplying the heat. So sinter is getting heated up, and after that gas do not have sufficient heat, so gas cannot heat this region, but it can dry it up, so it is a drying zone. And then there is a cold charge, because now when the gas comes through this dry zone, then it doesn't have any heat to give to the charge, so it remains cold. But when the combustion zone will shift here, then this zone again will become drying zone, and then slowly it will be preheated zone and the combustion zone will move. So this is the way, and the temperature profile will look like this. Here the solid temperature increases and it attains the maximum, and again the solid temperature decreases like this. So you can understand what is the mechanism of heat transfer and how the temperature profile. Now if you see in an actual plant what happens, this is basically industrial moving sinter bed. In that case you can find, instead of that is here you can find the fire line. How does it move? This is called the combustion zone, or you can call it fire line or flame front. So it moves layer by layer, this layer and then this layer, this layer. But industry, this is the fire line. It moves like this in inclined way, because you have a horizontal component of velocity. So fire line moves like this. This is the fire line, and finally at the end of strand, your fire line has to reach the bottom, otherwise bottom part will not get sintered. Okay. So there are two important terminologies are there. One is called the fire line. As I said, this is the fire line in which it moves into the sinter bed. And another terminology is called the burn through point, the BTP. BTP is when basically the fire line reaches the bottom of the sinter bed. That is called the burn through point. At that location of the strand, BTP has achieved, you can say. So BTP is usually achieved. That is the fire line reaches the bottom of the sinter bed just 2-3 block ahead of the end of center. Okay. So suppose it is the end of the strand. So fire line should reach here. That is before it reaches, and then the sinter get some time for cooling, and then it get cracked. It is broken, and then it is deposited somewhere, and then it comes out. Now this BTP is essentially, it has to reach at least before the strand. Okay. If it doesn't reach, if the BTP is not reached, that means at the end of the strand, that means there are some sinter mix is there which has not been sintered. That means the peak temperature has not attained, because fire line has not attained there. So those will go for the return sinter. That's why you have to ensure that BTP is reached just before the strand. That is very much important. And if BTP is reached prematurely, suppose here the BTP has reached at this point, that is also not good, because a lot of strand will be unutilized. You can easily shift this BTP from here to here, such that your productivity also become more. Because if reaching BTP much earlier is also not good, premature attaining the BTP, and post attaining the BTP is also not good, because in that case you are not getting the sinter. So burn through point is the point where the point or the location of the wind box, basically where where the fire line has reached the bottom of the sinter bed, right? And how do you know this BTP in the industrial plant is that because you cannot insert the thermocouple in the moving bed, it is quite difficult. That's why it is basically indicated from the wind box temperature. So if the wind box temperature also increases as you move across the strand, and it comes to a peak temperature, and then again wind box temperature will decrease because of cooling of the sinter bed. So think is that where the maximum, because there is the maximum temperature of the wind box indicate that is the fire line has reached the bottom. That's why the wind box temperature is also high. So from there you can basically determine where the BTP is. So now the phenomenon of matching is very important. As I said, that is the preheating. That is the, as I said, that is the, when the gas passes through the combustion zone, it completely preheats itself, okay? And then it has sufficient heat capacity of the gas, it supplies the heat to the solid material and it gets preheated. So maximum preheating takes place just below the combustion zone, whatever the sinter mix is there, that get preheated to the maximum extent. And then it will burn. So when after the combustion zone, next layer will be burned next time. But thing is that your preheating and the rate of preheating and the rate at which the fire line is moving, if the match, then your temperature, peak temperature will be the maximum. Okay? That condition is called the matching condition. So basically matching when the rate of preheating becomes equal to the rate of fire line movement, right? Because that is the thing. So now that's why that is called the heat wave front. Heat wave front, that is the when the velocity of the heat wave front, that is the preheating front, become equal to the velocity front, the VFF, right? Now think is this is the simple heat balance if you do, and then basically if you do the heat balance, you get this thing. So how do you get the heat balance? Basically this is in the denominator you can find basically there is the heat capacity of the solid, okay, there is the say kilocalorie per kg per degree centigrade per normal meter cube. This is Ws is the kilocalorie per normal meter cube degree centigrade. So and this is basically the volume of the solid. Epsilon is the voidage. So 1 minus epsilon is the volume of the solid per unit volume of the bed. So okay, volume of the solid per unit volume is the dimensionless number, and this is basically kilocalorie per unit volume of the solid, right? So you can get then this denominator is basically the kilocalorie per volume of the bed, per unit volume of the bed, and this is basically VWH is basically the velocity of the preheating front. Or do you then, or the basically if you multiply it by the unit area of the bed, then this is basically the volume that is getting preheated, the volume that is getting preheated. So this is if you multiply this thing, so this basically VWH Ws into 1 minus epsilon is basically the heat requirement by the solid, okay, heat requirement by the solid, and the numerator is basically this is the heat capacity of the gas multiplied by the volumetric flow rate. So that means basically this is the rate at which your that is the heat is being supplied by the gas. So this if you equate, then you can find this thing. So this is basically you can get per unit time, everything is there. Though basically if you multiply it, basically the kilocalorie per unit time it is coming, that is the kilocalorie per unit time that is supplied by the gas, and this into this is the kilocalorie per unit time that is absorbed by the solid. And when they equate, then your maximum heat transfer take place. So at that condition, the velocity of the preheating rate, okay, that is the VWH, also called the heat wave front velocity, okay. So that is the velocity of the heat wave front when you get the maximum preheating, right, when the complete heat exchange between the gas and solid take place. So that is the way the velocity of the heat wave is defined. And if this velocity of the heat wave become equal to the velocity of the flame front, then you will get the matching. Then because when you get the maximum preheating, then the combustion is taking place, that is called the condition of matching, and you can get the maximum temperature. Okay. So and then VFF, that is the flame front velocity, is depends on which parameter? Flame front, that is the when it depends on the reactivity of the coal as well as and the partial pressure of oxygen. Now reactivity of the coal remain constant because you are using the same material, coal material, so reactivity is constant. So what you can change, there is the partial pressure of oxygen, that is the volumetric flow rate of the gas. Higher the volumetric flow rate of the gas, higher will be the partial pressure, okay. So that it depends on. So basically the flame front is a function of volumetric flow rate of the gas, and you can find the heat wave also a function of volumetric flow rate of the gas. So for a fixed burden, you can maintain a Q dot for which the VWH becomes equal to VFF. So you can only simply control. So for a particular fuel, air and iron charge, there exists a certain partial pressure of oxygen that sets the velocity of the blast to be drawn that ensure the condition of matching, right. So that is the condition of matching where basically you can attain a complete heat exchange between gas and solid, and also then you can get the maximum peak temperature in the sinter bed. And the peak temperature is very important because if you get a peak temperature high, then your sintering or the bond formation also very good. So under matching, you can see matching and mismatching temperature profile. If you see the temperature profile, this is the temperature versus time, okay, temperature versus time at a particular location. If you see, this is the temperature profile, you can see. This is the temperature profile. With time, basically time means you are moving in the distance also, right? You can convert the time also in the distance. So or you can say at a particular location with time or with the distance also you can see. So, at a particular location the temperature will reach like this and then it will slowly go down, right. And then another time there is another adjacent location, there it will be, it is little offset, basically suppose it is the top surface and then below it, here it will after some time it will again reach it and reach the peak temperature after some time and then again come down. But all the profile if you see layer wise, top profile, top layer, then this layer, this is basically the top layer and then the next adjacent layer, then next adjacent layer. And if your matching condition is maintained, then you can find always the temperature profile is similar, only there is a lagging. This lagging is there because it appearing after some time or after some distance it is coming. So, the fire line is moving from here, then here, after some time it will come here. So, initially the temperature will rise and after some time will come peak and then come down like that. So, this is basically the layer wise how the temperature profile is evolving with time, right. And here you can find under matching condition when the peak temperature always will be the same temperature you can find. If you have a mismatching, that what happens, then first layer you have this, but the second layer cannot reach that peak temperature and the third layer cannot reach, it is further lower, fourth layer further lower. So, as you go down the bed you are not doing the sintering. So, matching condition, unless you attain the matching down the bed, the sintering will be very bad. So, that is very important and this area is very important. More is the area under the curve above 1000, this more the area better with the sintering, because sintering is done basically by incipient fluid, that is the fusion and agglomeration, right. So, this area you can see here all the layers, these are Ho, but in this case this is going down, here there is no 1000, all temperature is below 1000, all temperature below. So, sintering is not at all taking place below the line bed. Okay. So, matching condition, that is why important. Now, another thing is that Sinter mineralogy, that is very important. We are coming to the mineralogy, that is the what type of bonding and all this take place and what is the quality of the sinter, you can correlate with the mineralogy also. Now, with increase in basicity, now what we are plotting is basically this is the weight percent at the CO to SiO2 ratio. Basically, when we make the sinter is basically and basic sinter. Most of the sinter are the basic sinter and then we need to know what are the bond formation there. Acid sinter means when there is no CO, these are the acid sinter at the depth you can see at this position. And what type of bond are there? Basically, there are silicate bonds are there, okay. And silicate bonds require little higher temperature because silicate requires higher temperature to form the, to make it liquid. The silicate temperature is little higher. So, you require a more fuel rate, more carbon is required to melt them and then make the bonding. And if you do the more use more carbon, what happens? In that case, hematite get converted to magnetite and partially to woodstite also. And then the starting material doesn't remain the hematite basically, because because as you will see the hematite is a better reductant in the blast furnace. If you use the hematite is a better reductant, better reducible than magnetite. Magnetite is not that reducible as hematite because when hematite convert to the magnetite, there is a huge phase change. There is the HCP structure become HCP to HCP to FCC because magnetite is FCC and hematite is HCP, and then when there is a conversion there is a volume change and it generates lot of stress and porosity into the structure that basically allows the gas for reduction and all these things. So, we want to keep in the sinter majority is the hematite, not magnetite, because if you do that and then when you start reducing the blast furnace, it generates a lot of cracks and defects into the structure that allows the gas movement into the sinter body, right. So, it is desired because hematite ore is more reducible. So, but if you use in case of the acid sinter when the silicates are basically the agglomerating phase or the bonding phase, okay. So, in that case you require more coal or more carbon you require, and carbon means if you use more carbon then you cannot retain the hematite into the structure, hematite convert to magnetite and then its reducibility decreases, and also you require that thing. Okay. So, basically with increase in basis, now if you want to make the flux sinter, what happens is that with increase in basicity, when you are moving in this direction, the crystalline silicates are progressively replaced by the glass and strength decreases. Thus acid sinter is stronger, and when you start increasing the base, then it forms a glass, because if you give lime, then CO, SiO2, Al2O3 other, they form say glass, and those are not very strong enough, right? Those are not very strong, those are glass. So, but it requires less coke rate. It requires the less amount of carbon, because glass is easily melt. You can melt at lower temperature. So, it's softened at lower temperature and make the bonding and all this thing. That's why your carbon rate become less. As a result, you can retain the hematite into the sinter structure, which remains reducible. So, it reducibility increases, but the strength decreases as you increase the basicity. That is one thing. And the strength become minimum at, there is the fuel rate decreases for low viscous glass and reducibility increases, as I said. The strength become minimum at a basicity of 1.4. At 1.4, the basicity become less. Why? Because beta to gamma transformation of dicalcium silicate. As soon as you add the lime, basically it forms the dicalcium silicate, and this dicalcium silicate, it transforms at basicity CO2 SiO2 ratio of 1.4. There is the phase transformation from beta to gamma, and that is a volume expansion, and it becomes very fragile. Okay. So, at that point the sinter strength become minimum. So, when is the acid sinter strength is very high, although reducibility is less, but when you go on increasing the lime, then its strength decreases, reducibility increases, but the strength become minimum at CO2 SiO2 ratio of 1.4, because at that point dicalcium silicate make a phase transformation from beta to gamma. As a result, it gives a volume expansion, it becomes fragile. But if you further increase the lime, then situation become different. This is the thing. So, strength further increases beyond 1.4. What happens is that you can find from here. Now, if you see the mineralogy diagram of this thing, as you go moving up in this direction, you can see initially it was silicates only. After that, as the basicity is increasing, you are introducing the glass, more glass is coming, okay, and more glass is coming. At the same time, you can find this is the magnetite, right? This is the magnetite, this is the hematite. So, magnetite you can find is the magnetite is decreasing slowly, magnetite is decreasing, and hematite is increasing into the structure. So, as you increase the lime, hematite is increasing, which is reducibility is increasing. That is very important to know. So, when the beyond 1.4, when you are going in this region magnetite is quite less, hematite is more. So, it is more reducible. And you can find beyond a certain at 1.6, beyond 1.6, then a new crystalline phases is appearing, that is called the calcium ferrite. So, calcium silicate is getting replaced by the calcium ferrite, and calcium ferrites are basically is very crystalline, and they needle like structure, and they hold the particle by their structure, they hold the particle, and then the bond become very strong in that case. Calcium ferrite, the crystalline bonding, okay, crystalline ferrites bond the particles together, and they are very strongly held. At the same time, fuel rate become less, because you don't require a very high temperature, okay, for melting and all this thing. Basically, the diffusion bonding become very strong here, and calcium ferrite basically hold the particles together, so strong enough. So, calcium ferrites basically formed, and also hematite percentage is very high, reducible, and the same time fuel rate also decreases, because crystalline formation does not require too much of fuel rate. So, you can find the glass almost reduced to 0. So, glass is also not there. So, no require of fusion, because here the crystalline calcium ferrite forms that basically hold the particle together very strongly. The strong sinter become very strong. At the same time, the fuel rate decreases. As a result, you have more percentage of hematite into the sinter, final sinter. As a result, its reducibility is also more, right? So, that is why the sinter strength further increases beyond basicity 1.4, and because glass is progressively replaced by the crystalline ferrite, needle-like precipitates holds the grains, okay. And also fuel rate decreases, reducibility increases, you can find from there hematite percentage is increasing, right. So this thing you can have books. So the matching phenomena is physically described better into the RH Tubkari Modern Iron Making Khanna publishers. And also Ekebishwas you can go through for the Sinter mineralogy, very nicely described principles of blast furnace iron making. So what are the conclusion here? Thing is that by sintering, iron ore fines are agglomerated to a strong and porous iron burden of certain size suitable for the blast furnace. That is the final thing, because it has a good strength, good reactivity, all these things, and it is much better than the lumpy ore. By attaining the condition of matching, when the rate of preheating becomes equal to the rate of movement of flame front, maximum sintering temperature, this is the peak temperature, can be attained maximum. So basically, under the condition of matching, basically you are making the full heat exchange between the gas and the solid, and also the rate at which the heat front is moving, that is the rate of preheating is moving downwards, is equal to the rate of your flame front movement. So as soon as the heat exchange become complete, okay, then you just set the layer on ignition the same time. As a result, your peak temperature become very high. If peak temperature is high, especially the area under the curve on the your temperature profile, temperature versus time at a particular location, when the area under the curve above 1000 degrees centigrade is high, then basically you can ensure a very strong sinter, right? And from mineralogy, CO to Si2 ratio is crucial parameter for sinter property, as I said, because acid sinter is stronger but less reducible. But as you make the basic sinter, its strength decreases because of glass formation, but its reducibility increases. But its strength becomes minimum at CO by Si2 ratio at 1.4. But beyond that, progressively beyond that, that is beyond 1.4 basicity, that is if I further increase it, then progressively glass is replaced by the calcium ferrite, a crystalline phase. As a result, what happens, the bond become very stronger, and also fuel decreases. As a result, your hematite percentage also in the final sinter increases, and your reducibility also increases. So flux sinter beyond 1.4 is good, both strength wise and reducibility wise also. And the sinter becomes stronger and become more reducible, as I said, at a ratio 1.6 when the glass is replaced by needle-shaped crystalline calcium ferrites. So this is all about the sintering process, and in the next lecture we will discuss about the pelletization. Thank you.